morning, all participants and dear Chairperson, Professor Sanong Ekasit, Committee for Supervision and Monitoring of the Development of the Half of Talents and Half of Knowledge in Engineering and Technology, and Associate Professor Dr. Atikom Lersabut, Chair of IEEE Photonics Society Thailand Chapter, and speakers, faculty, training organizer, and all participants. On behalf of the workshop organizer, speakers, faculty members, students, and participants, I would like to express our sincere gratitude for your gracious presence as the chairperson at the opening ceremony of the seminar and workshop on photonics in agricultural and food industry today. The Post-Harvest Technology Research Center, Faculty of Agriculture, Chiang Mai University, the Post-Harvest Technology Innovation Center, Half of Talent in Post-Harvest Technology and Particle Accelerators, Thailand Center for Excellence in Physics and National Electronics and Computer Technology Center have jointly organized seminar and workshop on photonics in agricultural and food industries. The objective is to provide experts, faculty members, and researchers interested in optical technology in agriculture and food with a deeper understanding of the technology capabilities and its appropriate applications in future agricultural and food research. The aims to extend research and academic service, as well as foster good relationships and cooperation among multidisciplinary experts, faculty members, and researchers. The workshop is scheduled on August 13 to 14, 2024 at Buskor Room, National Electronics and Computer Technology Center. This workshop has attracted more than 80 participants from various sectors, including educational institutions, research and development organizations, and the private sectors. This gives a unique opportunity for those interested in optical technology, agriculture, and food to meet, exchange ideas, and receive feedback among participants and speakers. We hope this will facilitate ongoing research projects as well as strengthen relationships among those interested in this field, further building scientific and technological communities in related areas. Now it's time for me to respectfully invite Professor Dr. Sanong Ekasit to officially open the seminar and workshop on photonics in agricultural and food industries, which will be an honor to all participants and speakers at this event. Thank you.
Dear Associate Professor Dr. Atikom Lersabut, Chair of IEEE Photonics Society Thailand Chapter, Dr. Noppadon Nantawong, Director of the Spectroscopic and Sensing Device Research Group, National Electronics and Computer Center. Actually, I am a researcher like all of you. I feel good today to come here and see some old familiar faces and also a lot of new faces today. I am a representative for NRCT today. On behalf of National Research Council of Thailand, I feel great to honor and pleased to be the chairperson for this opening ceremony on the seminar and workshop on photonics in agriculture and food industry. The National Research Council of Thailand, in collaboration with Thailand Science and Innovation Fund, has prioritized the development of mechanism to establish Thailand as a hub of science, research, innovation, both nationally and international level. This has led to a development of research funding scheme, right? The half of talent and the half of knowledge that used to support researcher to create a group of network of researcher in a key area of national importance. Half of talent of particle accelerator and half of talent for post-harvest technology, which co-host this seminar today and workshop tomorrow, is one of those important hubs that's currently being operated. In this seminar, the workshop will provide an opportunity for expert faculty member from university and researcher who interested in optical technology, in agriculture and food technology to gain understanding and knowledge about the capability of photonics today. This workshop will also allow speaker and participants to explore appropriate application of photonic technology for future agriculture and food research. In addition, it integrates cooperation between expert center, knowledge hub, research institute, and higher education institute for future research and academic service, as well as to strengthen relationship and cooperation between multidisciplinary expert, faculty member, and researcher to work together in a theme of transdisciplinary research. In recognizing this training, I am sensing that the organizer intention to present important knowledge to all participants. I sincerely hope that everyone will be able to apply this knowledge to improve the development of their research and in various projects in line with the objective of this training. I would like to thank the organizing committee and those who involved. For my personal message to all participant colleague, research colleague, research in half of knowledge and half of talent is a kind of a research scheme, funding scheme to initiate the collaboration between researcher among various institutes. Before this, Thailand, we have research hub, research center, center of excellence in each university, but they working separately and fighting each other for funding. Half of knowledge and half of talent is different. This scheme try to change those competition, those kind of enemy to be a friend, to be a colleague. So this hub and this training, I think it will be a good starting point for those collaboration. So it's my personal message to all of you. In the future, this hub of talent and hub of knowledge give some seed money is about 5 million a year, right? To organize this collaboration. But later on, what the committee want in the future is all of participants, all the team will collaborate, brainstorming, and come up with some new important and significant project to hunt down more bigger grant money from granting agency in Thailand and abroad. So the key success of this half of knowledge and half of talent is the member brainstorm and work in their area and at the same time have identified very promising research team and come up with a potential grant proposal to apply for more funding. I believe that many hubs try to do the same thing. So the agriculture industry and research in Thailand is quite big and important for Thai society. So I hope that in the near future, this team will come up with a very promising project, big one, and have impact to the society. And maybe you can hand down like a big funding, like 50 million or 100 million a year. It's possible. That's what the committee, the funding agency want. That's my personal message. So at this proper time, I'm delighted to opening this seminar and workshop on photonics and agriculture and food industry. And I hope you have a really fruitful meeting and come up with some new idea, some project, and hope for the big net granting for you guys. Thank you.
Professor Snong Ekasit, Chairperson the Committee for Supervision and Monitoring of the Development of the Hub of Talents and Hub of Knowledge in Engineering and Technology. Dr. Nopadon Nantawong, Director of the Spectroscopic and Sensing Devices Research Group, National Electronics and Computer Technology Center. Ladies and gentlemen, on behalf of the IEEE Photonics Society Thailand chapter, I would like to express our sincere gratitude for your gracious presence to deliver the opening remarks at the senior and workshops on photonics in agricultural and food industries, and for being part of the morning sessions lectures today. This event allows experts from the IEEE Photonics Society to share cutting-edge knowledge in optical technology and its appropriate applications in various fields. In addition, this event presents an opportunity for the IEEE Photonics Society Thailand chapter to foster good relationships with multidisciplinary experts, faculty members, and researchers from various organizations interested in applying optical technology to agriculture and food science. It also provides a platform to exchange ideas that will help drive research and development both domestically and internationally, leading to practical applications that will benefit society and the nation. Today we're going to have the talk from IEEE Photonics Society distinguished lecturer, Professor, quite hard to read the first name. I asked him many times, I could not remember. His name is Professor Tawfique Hasan. He is a professor of nanoengineering at the Cambridge Graphene Center, Cambridge University Engineering Department, and LIST Group. He's also the deputy head of electrical engineering. He gained his PhD in electrical engineering from the University of Cambridge in 2009. He also has a master's degree in engineering in analog microelectronics from the University of New South Wales, Australia. Professor Tawfique got his Bachelor of Science in Electrical and Electronic Engineering from the Islamic University of Technology, Bangladesh in 2001. He has held several research positions in the university since his PhD, including a junior research fellowship in King's College, Cambridge, a National Science Foundation China Foreign Young Scientist Research Fellowship, and a Royal Academy of Engineering Research Fellowship to work on graphene-based flexible and printable devices. The latter contributed to the foundation of Cambridge Graphene Limited, which was acquired by Versalin in 2017. He is an editorial board member of Advanced Photonics. Professor Hasan is a fellow of Optica. This year, he is a distinguished lecturer of IEEE Photonics Society. That's why we have him here. Thanks for coming to Thailand. Okay. And also, he is the Title C Fellow and the Director of Studies in Engineering in Churchill College, Cambridge. Okay, before we start hearing the lecture from Professor Tawfique, finally, on behalf of IEEE Photonics Society Thailand chapter, we would like to thank the organizing committee for honoring the IEEE Photonics Society Thailand chapter with the opportunity to participate in seminar and workshop on photonics in agricultural and food industry. Ladies and gentlemen, I think everyone eager to hear what Professor Tawfique is going to talk. Please welcome Professor Tawfique for his lecture.
Good morning, everyone. Thank you very much for the introduction. So my talk is going to be a little different. I'm not going to talk about agriculture in general. I'm going to talk about spectrometers, essentially a component that can be used for agriculture and many other applications. Now, this is part of this IEEE Photonics Society Distinguished Lectureship. So I'm supposed to talk a little bit about my career as well, how I am, where I am and how I actually have come here. And then after that, I will talk in general about spectrometers, what we have done to create a completely new type of spectrometers that could be used for a lot of different applications. So I'll start with my academic journey, so please bear with me. So I was trained as an electrical and electronic engineer, just like many of the other young researchers in many Asian countries. It is a common subject, and I did my bachelor's in Bangladesh in Islamic University of Technology, and that was from 1997 to 2001. After that, I changed the topic, but moved closely to electronics. So I've done analog VLSI design, so that was on microelectronics. And this master's was done in University of New South Wales in Australia. That was for 2 years, so research master's. And so I got a lot of idea about how to do research, which normally is not trained in a bachelor degree in Bangladesh. Now, what happened was that when I was doing this, after I finished this undergraduate degree, I was thinking about working on nanomaterials, and I applied for a lot of different PhD positions. And so when I started this master's, I got a PhD position, a PhD offer from University of Cambridge. So after I finished my master's, I started my PhD. I moved to UK, started my PhD. Oh, by the way, I forgot to mention that I met my wife during that time as well in Australia. Right. So I moved to UK for PhD, and that was from 2005 to end of 2008. And the topic was very different. And that is something that I wanted to highlight, that I have degrees in electrical engineering, that I moved to microelectronics, which has some sort of similarity, but then I moved to something on carbon nanochips and solutions and processes and for composite applications. And if you look closely, I've done work on ultrafast photonics, mostly using saturable absorbers. Those of you who are working on ultrafast lasers, you may know that's basically a type of material that will change its absorption property if you increase the intensity of light shining on the material. And that can be used to create lasers. So that actually, was quite a big change for me. And what happened was, I went through a quite difficult period when I changed this subject. And I'll come back to that briefly. Now, after that, after I finished my PhD in Cambridge, I changed to 2D material. So essentially graphene and other type of two-dimensional material. So this was one-dimensional material, and then I moved to two-dimensional nanomaterial. So the change was not that much. But what actually happened was I looked at physics, chemistry, materials, optics, and electronics. So I was no longer an electronic engineering student, but I was looking at a broad areas of subjects. And this is because I was looking at materials that can be then engineered to make devices, and then something that could be used in our day-to-day life. So I became this research associate, and I started working on solution processed graphene and 2D materials to make transparent conductors and other electronic applications. And then I became something called a college research fellow. So this was from King's College in Cambridge. And what this means is that the college was providing my salary. I was not funded by the department and not funded by some supervisor, but I had my own funding, my own little funding, not much, but that was the first step towards independence. And one of the important things for Cambridge is that when you get these kind of college research fellowships, this one was for 4 years, and I was able to take PhD students, even though I was not a formal faculty member. So I got my PhD student in 2011 to start my independent research career. And obviously, as you can see that from electronics, then solution process materials, I am now looking at inkjet printed electronics, photonics, and sensors, so more like printed electronics. And then, of course, I looked at other printing technologies and applications. I got a Royal Academy of Engineering Research Fellowship, which is one of the most highly competitive fellowships for young researchers in UK. Usually 4 to 8 people get it every year. So I got one working on graphene, and that enabled me to start my group properly and hire more PhD students. And I became a lecturer in 2013. Working on the same area, and that enabled me to actually now properly start my academic career. Then I moved into smart nano devices. Again, gradually, I was looking at printed devices. Then the holistic picture was, the same idea, but essentially expanding quite a bit. I looked at large area printed optoelectronics, photonics, and sensors. So the idea is now to actually enable these devices to be enabled by simple computation. So the key point is that the nanomaterials that we use for our devices are not really good enough. They have their limitations, they have their problems, even though they are unique in many different aspects. And what I'm trying to do is to actually use very simple computations to make them better so that they can compete with traditional devices. I became a reader or associate professor in 2017, and then became a professor in 2021. From there, I now formally looked into, started to look into computational spectrometers, sensors, as well as memories, and essentially moving more towards computational and algorithm-intensive systems. Now, this is, as I mentioned, that this is hardware software co-design for computational sensors and optoelectronics, and that is one of the key areas that I am interested in. I'm developing my academic profile. Now, as you have seen that I have changed quite a bit this way, that way, starting from engineering to materials and now coming back to engineering. And what I wanted to convey, because it's a IEEE Photonics Society lectureship, I need to talk about my career. I need to talk about the lessons that I learned. One of the most important lessons I learned is that the transitions are very hard. So when I moved from one subject to another subject, it was very difficult. It was very difficult to understand the new subject, the new ways people express their ideas, their opinions. But one of the most important things when I was actually going through this hard period is that it is important to acknowledge the weaknesses that we have when we change to a different subject. Because if we do not do that, then we will be stuck. We will be thinking that we are very good in the new subject as well. So the first thing, if we are changing subjects, is to ask for help. Ask for guidance from people who are experienced. And then we learn from others. Then we educate ourselves to a new subject. And the benefit that we get, and this applies to everyone, not only the young researchers, but to everyone here, is that once we actually come from a different area, learn and educate ourselves onto a new subject, we can then start recognizing our strengths. And the strengths are, because we come from a new subject, we have a completely new perspective. If you have somebody from physics background, and if your colleague has a physics background, and if you are coming from engineering, you talk with each other, you will see that you two think very differently. And this is because the way you are trained. And this perspective brings completely new ideas, completely new understanding, and most importantly, the new innovation. So if you have time, if you are a young researcher, and if you have time and opportunity to switch subjects, then I would encourage you to do that, because that will give you a unique strength that most of the other people will not have. And that is my message. That is what I learned during my academic research career. Right, so now I move to spectroscopy. So, the works that we have been doing on a spectrometer. So one of the most important things for us to understand is that when we are looking at analytical techniques in in a laboratory environment, there are quite a few different options for us, right? So we have got mass spec systems. We have got NMR spectroscopies, liquid chromatography, and also optical spectroscopy. Now, if we look at these things carefully, we will see that all of these devices have certain components or systems that cannot be miniaturized very easily. And that holds somewhat true for the optical spectroscopy as well. So traditionally, the optical spectroscopy systems requires a light source. That's fine. But you also need dispersive optics. You need some optics that will enable you to separate the different wavelengths of light, the different colors of light. And in most cases, you will need a certain distance to actually have a good dispersion of light so that you can then pick up individual colors of light to measure the spectrum of light, which is the job of these spectrometers. And that means it is quite difficult to make them quite small. And our task, what we are trying to do is to make them small. This is a very general slide. It's a very simplified version as well. So as we know that, we have our eyes and we can see only in the visible region, only a small part of the electromagnetic spectrum, right? But what we don't normally recognize is that our eyes, even though we are, if we have healthy, we have 3 different cells, our eyes are not very good in actually doing a lot of things, recognizing a lot of things that the light normally carries. So one of the strengths of our eyes is that although we have got 3 different colors, color sensors, we can pick up millions of colors very easily, right? So if you're looking at this color chart, we can pick up the individual colors. But what we cannot do is to know the spectrum that is producing that color. We cannot do that, right? We do not know. And this is very important because the spectrum contains a lot of information about the material, about the surface, and the other properties. Take some examples. This is, again, picked up randomly. So if you know the spectrum of this mark on the skin, and if you can do polarization measurement at the same time using very simple computational technique, you can detect early stage skin cancer without doing a biopsy. Very simple application. But this one is quite interesting. So even if you actually, if you have a completely camouflaged threads, that is very difficult to detect by conventional optical or other techniques. If you do it with infrared and polarization measurements, you can easily pick up these identified threads as well, which is very difficult just to do using thermal cameras. So these are just 2 examples of what our, if we can get information from light, what can we achieve? But perhaps most important point for us to actually recognize is that if we can make these spectrometers, these optical spectrometers, which are benchtop systems, if we can make them really small, they can do wonders for us. And this slide, again, picked up randomly to actually highlight how many sustainable development goals we can cover is just actually is amazing. So for example, if I just click, you will see that at least all these, the red ones, out of the 17 sustainable development goals can be impacted if we can achieve miniaturization of the devices that can measure the spectrum of light into different wavelengths. Again, picking up random examples, global crop yield increase is required to be about 2.4 to 2.5% by 2050. And we know that even after we are actually trying with genetic variations of the different crops and fertilizers and other systems, it is very important for us to actually work on the loss of crop. And this is one of the ways, if we can improve the current spectroscopic systems that are being used by drone agriculture, we might be able to at least make some contributions towards achieving that goal. I'm coming from UK. The amount of plastics we are actually sending to landfill every year is more than 2.5 million tons. And this is mostly because we cannot separate the 6 or 7 different types of plastics that our households typically produce. The CMOS images that we have in our smartphone would have done much more than taking beautiful selfies if we could use them to detect spectral signatures, especially for water and food safety, even within the visible and the near infrared region. And then, of course, everyone knows that there are a lot of things, a lot of harmful threats, especially our chemicals and biological nature, that could perhaps also be detected if we could develop miniaturized sensors and airports and other important areas of national security. So all these could actually be made significantly more impactful if we could miniaturize the spectrometers. Right. So what we normally do is to let me just show you how a normal spectrometer looks like if you're not familiar with it. So you've got an entrance slit where light comes from. You've got some collimating lenses, but the most important part is this dispersive element, which separates the light into different color. Right? So these light, let's say broadband light comes into different colors, hitting at different part of the screen. And what we have are detectors or detector arrays. The detectors themselves do not know what color you are trying to measure. It measures everything within a certain range. So when you have the green light hitting at a particular detector, it will just give you the intensity of light, but it doesn't know it is measuring green light. As a user, we will know that. So when this light is separated into a rainbow or a spectrum, then we can easily pick up the different intensity of light, and therefore we can construct the spectrum of this incident light. Very simple principle. We separate the light into different components, and then we pick up by detectors which cannot identify individual colors. Now you can make them small, really small, using the same concept. So in this case, you've got a chip where we have got an input light with an optical fiber. It hits a grating, and this grating will then separate the colors of light into different components. And as you can see that we now have multiple fibers, and each fiber then taking out individual wavelengths or colors of light. And therefore, you can create a compact version of this. The problem, the physical challenge, is how to separate the light efficiently in a very small space. And that has limited the size of the miniaturization of the spectrometers so far. So if you are looking at commercial systems, a commercial detector system, then this is perhaps the best one you can find, or probably there are slightly better ones from Hamamatsu and other companies now. But this spectrometer, the miniaturized spectrometer, uses the same principle. You have light hitting a glazed grating, and the grating then reflects the light into separate colors, and then this is then hitting onto the CMOS sensor, and you are picking up the different colors of light. And by that, you can have a rather okay spectrometer with 15 nanometer resolution, and this is its size. Now, these systems all use this dispersive component to separate light, but there are systems that can avoid that. This is one of the earlier examples published in 2007. And what they have done, instead of using these dispersive components to separate light, you now have filters on top of them. And the filters are very sharp, meaning that each individual filter will pass only one color of light, a very small, a very narrow wavelength of light. So you are, instead of using the dispersive component, achieving the same effect by using these filters. So therefore, the color that is actually coming through this filter array, so you have got a broadband light coming through the filter array, only a small part of the light, the wavelength of light corresponding to this will actually now be hitting onto the detectors underneath. And so if you actually measure the detectors current generated, you've got all these peaks, and from there, you will be able to construct the spectrum. Very simple concept without using the dispersive element. Now, because my talk is about the miniaturization of spectrometer, I want to just give you an overview of the different types, even though I already started talking about some of them. So the first one is the dispersive optics type. So you use the reflection, transmission, or waveguide dispersion, so anything that can then separate light into different components. And you can use that to create a spectrometer. This is another popular approach. A lot of people use it because the filters are now commercially available. So in this case, what you do is, most common filter is a variable filter or a tunable filter. And the idea is the same. You've got a narrow band filter, like the example I just showed in the previous page, that passes a very narrow wavelength of light, and you can detect using detectors that they themselves do not know what they're doing. But in the end, you get a spectrometer out of it, as per the previous example. Then there is this Fourier transform spectrometer, which essentially works by interfering two different lights to actually to create a pattern that can be then analyzed to actually grade the spectrum. But perhaps the more interesting one, because I'm working on that, that's why I'm saying it's more interesting, is a reconstructive spectrometer. And the idea is that you have got a an element or a material, we call it an encoder. The encoder then actually allows the light usually to pass through the material, and the light's property changes. And if we know the encoder's property, and if we then know what we are measuring using the detectors, we can calculate the spectrum of light, the incident light. And this is a very new type of spectrometer. And the main advantage of this is that you just need an encoder. But most importantly, you can measure not only just a spectrum, but if you can detect, if you can make a decoder right, you can measure almost anything about light. Not everything, but almost everything. Incident spectrum. The problem with this approach is that they still need a detector. They cannot be made extremely small. So they still are a centimeter, let's say, or a few millimeter by few millimeter at best. So what we tried to do when we started the work in 2014-ish, that we wanted to see whether we could create something very interesting without using any dispersive component and without using any traditional detector. So the idea came from the student who was from Zhejiang University, and he was growing these nanowires. And these nanowires were very interesting. So in this case, you can see one of these nanowires is basically a combination of CDSE and CDS, so cadmium selenide and cadmium sulfide. And if you control the positions of these two with respect to the highest temperature point in the furnace, you can get a band gap gradient nanowire. And what that means is that the band gap at one point is completely different compared to the band gap of another point, and this covers almost the entire visible region. And that is why you get to see that it looks like a rainbow. If you look at the atomic percentage, you can see that the CD, the cadmium, essentially dominates almost everywhere, about 60%. The sulfur content, it drops as you go along the nanowire. The selenium content starts from 0 to increases to up to about 35 point. So the whole idea is that it changes the composition as you move along. And that depends on how you actually grow the system, how you grow the nanowire. Now, the idea is very simple, that what we tried to do, the implementation was extremely difficult, took us 4 years. But the idea was that we have one of these nanowires, and we make many parallel electrodes with that. And those of you who are familiar with semiconductor materials, you will know that these individual devices, they will respond to light when you shine a broadband light because they're semiconductors, yeah? But this response will depend on the color, or essentially the band gap of the material. And because we've got a band gap gradient nanowire, meaning that individual devices are slightly different from each other. When you shine a broadband light, each of these devices will respond slightly differently. Okay? It's a very simple concept. So this is what we do. We actually use a tunable light source, and then we use a diffuser, power meter, a spectrometer chip to do a calibration, how each of these devices behave when we shine a broadband light. Yeah? And then from there, we can find these response. So individual of these devices, they will respond according to their wavelength in this fashion when we shine a light onto them. So this response function is very important because this is the key to what we have done. And this gives you a very simplified picture. So let's say we have a broadband light. Yeah? The broadband light is now shining onto this spectrometer. And what we now have is that unit 1 in this device will now create a unique current I1. The same light will create a slightly different current because the material is different. It will create a current I2 and so on. So all of these, it will create some unique currents. And because we know the response functions that we already have created, we can combine them together in this fashion. So you've got a response which comes from an originally stored already. We now have an integral response that is now manifested as a current from that unit. And we can get an equation from individual units. So where we have got the wavelength range, we have got the light that is unknown. We know the response function, and that gives the current I1 from that unit. So in our case, we get 38 equations like that. Yeah? And these equations, they are not very easy to solve, but there are fortunately some very simple regularization techniques. So we used adaptive technology regularization. We didn't need to change much. It's a common method to solve equations like that, and you can then approximate the incident light, and that is completely through mathematical methods. Okay. So that is why it is not just, you're essentially combining many different optical devices. Simplified version is they are essentially optical sensors, and you are just combining their output to create a device that are very different. So you can then use it to detect single monochromatic peak, and you can use 38 units, you get up to about 7 nanometers. So it's not really great, but still quite impressive, considering that it's only a couple of 100 micron long, the device. The double monochromatic peak separation can be about 15 nanometer, and we found that this is the resolution, the maximum resolution we can get from our device. It can detect somewhat the broadband light, and also it can actually represent consistent operation across the visible range that we were looking at. One of the interesting things is that because we are looking at all these devices, if one of them fails, we could create a very simple failure mode in our algorithm, and we could use that to see that even if actually one of the devices or units fail, the other units, because they have overlapping response functions, they can easily identify the failure, and as you can see that the output barely changes. So this is how the spectral image setup looks like. So I've got a tunable light source, diffuser, power meter, that's the chip, and that's all basically the electronics that drive these sensors. So of course the device itself is small, but the electronics that we made, homemade electronics, they were quite not really small at that time. Very simple applications. Our was a single pixel spectrometer, and if you want to carry an image, we could actually use scanning across an image plane. So in this case, we imaged the part of the university logo. And from there, we can see that if we took at the constructed spectral data cube at different areas after scanning, we could get an image like that. And that can easily identify the different areas with completely different intensity and the spectral profile. But the interesting thing is, even because the spectrometer is very small, you do not need a lens to image very small subjects. So in this case, we try to image an onion cell. Onion cells are quite large, almost similar size compared to the nanowire itself. And what we did is we used a shift register strategy where we had overlaps between the nanowire device as well as the cell that we were trying to measure. So if we do this overlap with the shift register strategy, we could create these data cube of the normalized absorption of the onion cell. So in this case, it was more like an absorption measurement because the onion cell was here between the light source and the chip. And as you can see from the microscope image, if we look at the different regions of these spectral measurement of the data cube, you can see that at different regions, you've got completely different absorption profile, indicating that it can identify the different regions in the cell. Now, the whole point of doing this spectrometer is that to make it small, right? The philosophy is that we have 38 devices, they are individual, and we can combine their output to create something that individually they cannot achieve. Now, imagine that you've got one device, and that one device could be now tuned to represent 38, 40, or maybe 100 different states. You could achieve the same thing. So this is what we did with Professor Tawfique Hasan from Aalto University. So what we tried to do is we had a single device based on two different two-dimensional material, creating a van der Waals interface. So essentially, it's just the interface, the semiconducting interface here. And if we apply voltage, we will change the interface. It becomes a new photodetector. And we can do that again and again and again, and we can create many different states to achieve the same thing, but in this case, using a single device. So this is how it looks like. I will quickly move to that. So, well, the device does not look as pretty as before, but the idea is the same. So you have got the boron nitride. So you've got graphene, then you have got a boron nitride, and essentially you have got this WSC2 and MOS2. These are the two different semiconducting materials. They're monolayers or few layer materials in this case. So we actually create these heterostructure, one sitting on top of another. And if we apply a voltage, then you can tune the interface between them. And that means we can get new type of photodetection capability. And so in this case, you can see that we are changing the voltage, the gate to source voltage that changes the current. and that shows that you have got different variations in the response functions that can be used to achieve the same thing that we have done in our nanovirus spectrometer. So it can done this single junction spectrometer performs very well in terms of creating, measuring the monochromatic spectra as well as broadband spectrum. But perhaps the most important thing is that you can see that the peak wavelength accuracy is actually very good. Well, within the short range, it is close to a nanometer or so. But in this case, you can see that our achievement took us to somewhere here. So it started to overlap commercial spectrometer systems in terms of spectral resolution and the NPDR change per wavelength. But most important thing is that if we could achieve the response that was already published by literature by other groups, we would actually have been sitting somewhere there. Therefore, there is a possibility that if we could improve the interface and the material system, we could actually achieve much better resolution. Those two devices are the smallest possible spectrometers that have ever been demonstrated so far. This is just another recent example we have done. In this case, a van der Waals similar material system, van der Waals tunnel heterodiode spectrometer. So we have got now MOS2 and black phosphorus, two different materials. The main point is that the black phosphorus now is, it works beyond the visible region as well. And therefore, we can use the two different modes for visible region and for the near infrared region. And in both cases, because it has BP is a semiconducting material, MOS2 is a semiconducting material, you can actually have a tunneling effect when you are actually doing the reverse bias mode. And therefore, it works reasonably well, not as good as the previous ones, not only in the visible region, but also in the near infrared region. And this is one of our attempts to extend the wavelength region of this kind of spectrometer. The critical challenge in all these, fancy material-based systems is the upscaling. Nobody can make them, in an array form where we could image something that could be useful for real applications. So to just actually cover that part, what I can show you is the advancement trajectories of spectrometers over the last, couple of decades. And what we see are quite interesting. And this actually, if you are following technology trends in general, this will make perfect sense to you. So in 1980s, when we were actually looking at spectrometer, not we, but people were looking at spectrometer as a concept, you see that most of these devices, they were progressing with respect to the progress in the CMOS processing technology, the computing, the digital electronics, or the MEMS-based technologies that were really flourishing at that time. So you have got MEMS-based systems, you have got gratings and tunable filters, all took the advantage of the processing technologies that time. And that went on quite a bit. Even in this case, for example, you have got a MEMS tunable filter. So basically, practically reducing the gaps between two plates. And what happens is that this grating spectrometer that was first demonstrated in 1990s, it became commercialized in 2015. So it took quite a while. But that was the Hamamatsu's grating based on that concept. Now, you can see that over the years, there are a lot of different technologies, especially magenta interferometer, etc., started to develop when silicon photonics really took off. But in 2005, you've got this computational device, the broadband array spectrometer. And then there were other technologies with digital magenta and single photon grating and so on. And we published our first paper in 2019. Almost at the same time, there was this work on the metamaterial filter array spectrometer. And the idea is very interesting. And if you remember, in this case, we were using broadband materials mixing together to create a broadband response. This metamaterial was actually achieving exactly the same thing. So in this case, what Professor Yideng Huang's group did was to create a series of metasurfaces. And each of these metasurfaces were designed in a very specific way, following simulations. And what essentially you do is from these metasurfaces, you get different responses. So instead of using these quantum dots, mixing them together to create a broadband response, you now have metasurfaces creating this broadband response. And the idea is exactly the same. These are broadband responses. You use them to compute the spectrum of light. So they have a startup company which was doing pretty okay after COVID. I visited them last year. And the most important point for them is that it is similar to the quantum dot filters that I previously showed, what was published in 2015. But in this case, these metasurfaces can be precision manufactured. And that changes the whole thing, because that can be then now, these can be now made in, manufactured, mass manufactured. So the point is, even though they are very similar, this is a new technology, but we still have a problem. The problem is to design a computationally efficient metamaterial filters or encoders. Because what they have done was to create these encoders, but they are not computationally efficient, meaning that they have a lot of empty spaces where you are actually repeating the same patterns from here and there. What we ideally need are these filters which will encode the maximum amount of information available from light. And that is something that we are trying to actually achieve now. So let's go to that. So we have started looking at some computational systems. Let me see how much time we have. Plenty of time. So I don't have that much to cover, so don't worry. So what we are trying to do is now to create these encoders or filters in a way that will now capture maximum information of light, right? And to do that, what we need is that the response functions or these absorption peaks that I showed you, they need to be unique, completely separate from each other, so that you can capture maximum amount of information using minimum number of these filters. So this is one of our attempts. One of the master's students actually did that based on a paper that was already published. So what we have is basically we take the hyperspectral data from publicly available database, and then we try to train a system, and the system can actually spit out some optimized encoder response matrix, which is what it means is that if we actually give the publicly available hyperspectral data, let's say in this case 400 to 800 nanometers, this particular system can actually tell you what are the response functions of the metasurfaces that are needed to get very good reconstruction of the incident spectrum of light. So in this case, we get these series of encoder response matrix, and each of them basically tells you, oh, your absorption needs to be exactly like this, and you get a perfect, if you have 20 of them, you get a perfect spectrometer. Now, we then actually try to trim some of them, because the more of these the response matrix you have or the metasurface you have, the more computation you need. So we trimmed some of them, and essentially it would look something like this. These are not real, but this is what it would. It would actually look. Each of them are very unique, very different, with high and low absorption and absorption or the transmission peaks. And we could then use them to create a metasurface. So in this case, we created these 25 encoders at first. We didn't really want 25, so we removed 7 of them. So we are somewhere here in terms of the contribution, so just about 85%. So you can see that these are the functions from the system, which does not know what is a spectrometer, which does not know how the whether it is possible to make them or not. But these are just some mathematical representations of how these devices would look like if you were feeding the publicly available data. And if we could create these metasurfaces, we would be able to then capture the maximum amount of light with minimum number of these metasurfaces. And that is the key point, that minimum number of metasurfaces. And to achieve that, we then actually need to look at something called an uncorrelation factor. How these different metasurface units are completely separate from each other. So in this case, our average correlation value is 0.23. We targeted about 0.5, meaning that so this part and that part is completely symmetric, meaning that each of these individual metasurfaces, they were completely separate from each other, or close to completely separate. So these are just some training set and test sets, basically. So if you train the system, and you can actually then try to see whether the system can replicate the data, without seeing them. And this gives you some better understanding of what actually it does. In terms of the wavelength, we considered from 400 to 800 nanometer. Again, all these things are in simulation. You can see that the deviation or the peak wavelength accuracy of the spectrum that we are trying to measure is less than a nanometer. if you are looking at the width of the lines that we might be able to detect, you can see that if the width is small, so FWHM is small, then the data is more correlated. But as the width becomes bigger and bigger, which is typically the case if you are looking at agriculture and other areas, then the deviations can be quite large. And that can be then actually looked at in this. So if you are looking at a full width of maximum of 1 to 4 sub-nanometer, and then if you are actually there, it is a little bit higher than the smaller case. So still, they are all below 1 nanometer when it comes to the reconstruction. Now, this is quite an interesting thing. So we created these 18 spectrometers, all in simulation, right? And we then actually feed it to the system. We have some data and says, okay, so reconstruct it using these 18 filters that we have created. And as you can see, that it actually replicates things pretty well. Yeah. Of course, we've got a lot of in the input data, we've got a lot of noise, and the predicted data, or the simulated data actually smooths quite a lot of noises, but it actually matches pretty well with what we the input and output are quite good. So they are fantastic because we now have 18 different filters that can create, in our understanding, perfect spectrometer between 400 to 800 nanometers. The only problem is, even though they are computationally efficient, but they are not possible to physically realize, because if you are working, some of you are working on meta surfaces, you know that the filter designs that I demonstrated before are impossible, physically impossible to actually create. Yeah. So what we are now trying to do is to incorporate physical models to make them more physically aligned so that we can fabricate them and test our theory. Right, so that's where we are. I think I'm going the wrong way. Don't worry, I'm almost there. What I wanted to show you, the last slide is, obviously we are here and we are trying to improve things. The last slide is just to actually give you an understanding of the areas in general. So when you are, and this is mostly for let's say young researchers who want to do something about spectrometers, make them small, not only for agriculture but for any technology that can help not only Thailand but globally. Yeah. So one of the important points is that I do not consider them challenges. I consider them as opportunities. Yeah. That is very important. You set your mindset that these are opportunities that you can create. For high-dimensional, computationally efficient images. So if you want to create an imaging system, ours was a simple pixel-based system. If you want to create an imaging system that can measure the pixel-by-pixel spectral profile of an image, then we could perhaps look at all these. And this is not just a spectral, I'm talking about high-dimensional system. And therefore, it could be also polarization or even phase, right? One of the important things is that, we should choose areas that we like. So one of these, there are 4 different components that you can contribute as a young researcher. One is as an optical designer. And the key point for you, if you want to become an optical designer in this area, is that how to capture or encode the information from light. And these need to be optimized, as I have described in the last few slides, so that you reduce the computational burden. Yeah, because if you reduce the computational burden, you can image much faster, much better, with a much high resolution. And of course, they need to be manufacturable. So that's the first part. If you want to be an optics designer, these are the things that you may want to do. If you like materials, again, the idea is that how to capture encoded light, because the way you can do that is to look at the different materials to create photodetectors, dispersive interface that can separate light into different components, or the tunable junctions. You also need to look at broadband detectors, something that can measure not only in the visible region, but in the near infrared, and also at least up to the shortwave infrared region, which is key for agriculture and many other applications, especially in sensing. And of course, these kind of detectors need to be temperature sensitive, manufacturable. This is a very difficult area to work, perhaps the most difficult area in the entire picture. And they are highly competitive areas, and they are also related not only to sensing, but also to many military applications. And therefore, the technology is quite restricted. Then there are a decoder, somebody who likes computation. So what is the best way to interpret the data that you get from that and that? So you need to be good at mathematics. You need to understand mathematical or machine learning based reconstruction. And then you can also avoid this computation by using fingerprinting. A very clever technology that I don't have time to talk about, but essentially you are not blindly reconstructing the entire spectrum, but you know what material you're detecting and you focus right there, and therefore the computation becomes much more faster and more efficient. But this can be really useful, for example, for plastics detection or image disease diagnostics. And finally, system development, how to make things work. So this is usually, somebody told me that this is the job of the supervisor who does not do anything but just complains, do this, do that. But essentially, what you actually need to do in this case, how to make all these three different elements work in terms of integration, data processing, and application-specific scenarios. So there are all these important areas that you can contribute if you are passionate about not only application, but actually create changes, create new technology that could be used for many different applications. And finally, there was a very interesting paper that was published in 2024, and we also wrote a Nature Photonics news and views on that, and that is a very new way of doing exactly the same thing that I'm mentioning here. So that's our team. Very small team actually, because we have got only 2 students, Zhesheng and Ziying, who are working on the spectrometer. Others are working on different types of sensors. And we are always looking for new members. We have these many students graduating, and some of them are almost graduating. I think 4 of them are graduating soon. Thank you very much for your time. And I think I'm a little bit late, but thank you. Any question, comment?
So for my understanding, so the smallest spectrometer you get now is from nanowire, right?
The single junction spectrometer even smaller. It's a few micron by few micron. The second example that I showed, the electrically tunable van der Waals.
I still not quite okay. For nanowire, I understand. Okay, in 1 pixel you have minimum nanowire, and you get a spectrometer out of that.
1 nanowire gives you 1 pixel.
Yeah, 1 nanowire, 1 pixel.
Yes.
And we combine like many nanowire like together, and that's very small, right? So
yes, we can, but the problem is it is very difficult to create an array if you want to get an imager. To get an array of nanowires, you get the electronics of the electrodes out to create an imager. Okay. It's a very big challenge. The other challenge is the amount of data that we will get. So I talked mostly about, when I say that it is difficult, I talked mostly about the manufacturing side. When it comes to the data side, I was trying to talk about the efficient computational reconstruction so that we have less number of nanowires to actually get a much bigger, easier to actually compute the data. Less number of, not nanowires, less number of pixels that we are getting. Instead of 38, we want to have, let's say, 10.
Okay, so another question is there any like theoretical limit, like how small it can get?
Theoretical limit, very interesting question. Yes, and also no. What happens is that if you are looking at a nanowire, we are making these individual units that are photodetectors, right? The limitation is how much light it can detect and what is the noise margin. If the noise is too high, it is not going to work. So let me just very quickly show you one thing. So here, you see there's all these are responses, right? Responses from different units. If these are too small, then the noise margin will be such that the line will not be here, but will be crossing the upper and other lines, other devices lines. And that will create the problem because then the devices will not work perfectly. So if we want to create the noise margin small, the devices need to be large enough, or the light intensity need to be good enough. So in our case, I believe we did a calculation in the paper. I don't remember exactly, but I believe that we could get up to about 100 devices per nanowire of about 100 micron or so. So 1 micron, less than 1 micron, if you consider the. That's a fundamental limitations. Otherwise, you need to cool the device to make it better.
Thank you.
Yes, I wonder how narrow of the spectrum that your device can detect.
Right. So in this case, it was not. So you can see that for the nanowire, which was done about 5 years ago, for 30 units, we could get 8.5 nanometer. And for 38 units, we got about 7 nanometer. And the 3 nanometer was, actually, we say commercial, conventional spectrometer is the conventional, the small spectrometers that you can get. Ocean optics in our case. Now, we call the resolution in this case, the ability to measure 2 peaks, which is separated. So in this case, it was 50 nanometers. So that was for this. For the second example with the van der Waals, I think it was smaller. I don't remember the number, probably 3 nanometer.
I asked because my major is about optical communication, family with dense wavelength division multiplexing, and the spectrum is quite narrow. So I wonder if I can use your device applied to my application.
Yeah, it is difficult. So for example, if we are doing gas sensing measurement in the mid-infrared region, in the visible to near infrared might be possible, but in the mid-infrared region, peaks are very, very sharp. We won't be able to detect it, not yet. But one of the advantages is like, I give this example to many people. One of the advantages is like, it is almost like your computer. You update your Windows or Mac or whatever operating system you're using, it gives you new functionality, new performance. In this case, when we started writing our paper, our resolution, so the 50 nanometer was actually 25 nanometer. We improved the algorithm to get to 15 nanometer. So that's one thing. The hardware and software, when we are actually putting things together, the hardware can go up to up to a certain point. Software, of course, can go up to a certain point, but you can improve it to actually make it a little bit better. In terms of narrow line width, like a sub-nanometer line width, we will need to work quite a lot because these are all computational devices. It will take some time for us to get there, but I'm sure, especially with metasurfaces, we'll be able to achieve that.
So it seems like if we want to use your devices, we need to combine the computer software. I remember the last slide. You mean like how, if you want to make it like the device, do you have plan to make like embedded system in your chip or something like that?
So these devices, let's say the nanowire and then the van der Waals devices, they actually use an algorithm that can be hardware based. Now we do it with MATLAB. Yeah. And in fact, the company that came out from metasurface based design from Tsinghua, they actually have devices that are, I believe, a few millimeter by millimeter size that can also do the computation. So yes, it can be made small.
Okay. And my last question, you said you need a new member. If you want to send my student, do you have the plan of funding or scholarship for my students?
So yes, I'm always looking for new members who actually work really hard. So that's the catch, right? Yes, I'm always looking for members. In our case, for Cambridge, usually the competition for scholarships is extremely high. So they usually have to be within the top 1 or 2% in terms of academic results. And then obviously depends on how well they do in the interview, etc. But yes, I'm always looking for new members. And we're very happy to get someone from Thailand. Did I mention that my wife is Thai? Yeah.
If I don't get you wrong, I think the light that you are talking is a visible light.
Yes.
So I would like to know if it is possible to use your detector for detecting some other regions like Tesla or NIR.
Yes. So two points to remember. The technology itself, the platform itself, can be used to move to any wavelength region we want. but the material is the limitation. Yeah? If you are looking, for example, at short-wave infrared region, it is very difficult. Near infrared, we can use traditional nanomaterials that can cover, for example, black phosphorus example I gave you. Yeah? When it comes to short-wave infrared, there are several challenges. First challenge, and most important challenge, is the detector itself. And that is what I tried to mention in the last slide, that the most difficult challenge will be to find a detector that is cheap. Current mid-infrared, forget about mid-infrared, short-wave infrared detectors are not cheap. Yeah. So if we can make it cheap, it's fantastic. Otherwise, we will actually have to look at new materials or systems. The reason these devices are expensive, not because of the materials itself. In many cases, it's because of the volume production. So if we actually show a few applications that are really groundbreaking, I am certain that, especially up to short-wave infrared, we will have detectors not as cheap as CMOS, but should be quite cheap. People have made detectors with lead sulfide quantum dots, commercialized detectors, and with silicon graphene. I know that people use them. You can buy them and they work in the laboratory very well. So it is possible. And forget about the bulk semiconductor-based systems that are very restricted now. So it is possible, but the only problem is, they cannot just make 1 or 10. They need to make millions. And only then it will come down. And only then we will be able to use them for everywhere, every application. That is one way. There is another way where you can derive them mathematically. I don't know, I'm not very good at maths, but the idea is that, very simply, that the filters need to have response functions that will vary as much as possible, and they cannot be periodic, aperiodic response. So you have got, so the general principle is you create a response function like that. The second filter that you now create need to follow the same principle, but need to be very different from the first filter in terms of amplitude, in terms of phase, in terms of the spacing. And again, the third filter will need to exactly follow the same recipe, but need to be very different from the first to the second. So yes, mathematically it is possible, but we have not tried that yet. And this relates to only spectrum. If you try to do phase, let's say if you are doing full-Stokes polarization, things can get much more complicated. So machine learning probably is an easier option because it's, you just pass it to somebody else, not to you.
So first of all, thank you so much for the very interesting talk. And I think it's really inspiring, especially in the aspect of training the filters using machine learning. So what I'm curious about is how do you collect the training data from the various sources? Because it seems like the spectra can be different in terms of the output of the spectrum that you are collecting. So let's say it can vary, it can be varied by the temperature and the external surroundings that you cannot control. So how do you handle that situation?
Very, very interesting question. So in our case, the student who actually did the work had a computer science background. She had absolutely no idea about the spectrometer itself. So that's good because she didn't have to worry about these things. But the important point is that when you look at publicly available hyperspectral database, the data spacing is also very big. So some cases you'll have 1 nanometer, some cases you have got multiple nanometers and so on. And of course the range. So what we did was we actually normalized everything. So, we had, in our case, we had 1 nanometer spacing. We created them by ourselves. We downloaded the data, we modified the data to create these spacings using simple interpolation. That was the first thing. In terms of the additional light, we did not do any modification. In terms of the noise, yes, we did pre-processing because even in hyperspectral data, sometimes, because they are measured, not estimated or calculated, there are significant unphysical noises sometimes. So we cleared all those things before we actually attempted the machine learning.
Right.
Does that answer the question?
Yep, that makes sense. And that answers my question. Thank you so much.
Thank you. Thank you very much for patiently listening to me.